Hello, my name is S.J. Park from Ateneo de Manila University, and I will be presenting as research of Dr. Stuart Licht and his group from George Washington University entitled One-Pot Synthesis of Carbon Nanofibers. Industrialization has brought great progress in economy as well as science and technology, which shape the world we live in today. But this progress did not come without costs. Consequences of global warming due to increase in production of greenhouse gases is prominent all over the world today, from melting glaciers and ice caps, rising sea levels, unpredictable weather patterns to name a few. For the past decades, there have been numerous studies and developments in reduction of our carbon footprint and CO2. What if there's a more direct way of reducing CO2? Or what if CO2 can be made into something more valuable and useful? Dr. Licht and his research group have developed a novel method of capturing CO2 and converting it into oxygen and carbon through electrolytic synthesis using molten lithium carbonate. Carbon fibers form during the process, and the conversion is carried out with low energy input. They also calculated that using this method in conjunction with solar power generators in an area about 10% the size of the Sahara Desert, CO2 concentration in the atmosphere can be reduced to that of the pre-industrial revolution level in just 10 years. Let's look into how this electrolytic synthesis works. Galvanized steel wire cathode and nickel anode is connected to a power source and are submerged into molten lithium carbonate with temperatures of 730 degrees Celsius. To initiate this synthesis, initial current of 5 milliamperes per cm squared is used and slowly increase up to 100 milliamperes per cm squared. In this process, molten lithium carbonate decomposes into lithium oxide, carbon, and oxygen. Small amount of dissolved nickel near the cathode works as an incubation site for growth of carbon fibers, while oxygen is released back into the atmosphere. CO2 readily reacts with lithium oxide, forming and replenishing lithium carbonate. As the cycle continues, more CO2 is absorbed, more oxygen is released, and carbon fiber grows slowly. Different characterization of the sample were carried out. Scanning electron microscope image displayed that the team was able to grow uniform carbon fibers with a width ranging from 300 to 1000 nanometers and the length ranging from 20 to 200 microns. Results of energy dispersive spectroscopy showed that pure nickel was present near the cathode and pure carbon was present for the remainder of the fiber. X-ray diffraction results also confirmed that produced carbon fiber was highly homogeneous. Carbon fiber has impressive mechanical properties compared to conventionally available steel. It is stronger, more rigid, and lighter, which makes carbon fiber a favorable material in aviation, aerospace, and automotive industries, as well as high-end sport equipments and wind turbines. The major downside of carbon fiber is that it is quite costly to produce. Most commercially available carbon fibers are made from polyacrylnitrile, which is also known as PAN. The fibers go through several steps of heating, which include carbonization at 800 degrees Celsius and graphitization at 1100 to 3000 degrees Celsius. Dr. Lake presented an alternative way of producing carbon fibers, the solar and thermal electrochemical process carbon nanofiber, also known as STEP CNF. STEP optimizes both the solar and thermal energy collected from the sun and converts it up to 34 to 54% efficiency. As shown in the diagram, thermal energy from the sun is used to heat up the molten lithium carbonate, and the solar energy is converted into electricity. This results to 30 to 100 times less energy input during production of carbon fiber compared to the conventional methods. The tropical countries such as the Philippines is an ideal area to set up the STEP CNF, as these countries receive an average of 10 to 12 hours of daily sunlight with higher intensity as they are closer to the equator. This would not only help the environment but also help boost the economy, as the value of coal is about $60 per ton and graphite is about $1,000 per ton, whereas carbon fiber may range from $20,000 to $100,000 per ton. Related to this research, Dr. Lake published a patent on STEP, which was published January 3, 2013.